In this video, I will be talking about composite functions, how we compose two separate functions, and also how do we find the domain of composite functions. So the notation for composite functions looks like this. We read this as f circle g of x. Sometimes this is read as f of g of x. Either way is appropriate. I'll mostly be saying f circle g of x. And what this means, what this notation means, is we are inputting the g function into the f function. So let's look at a couple examples and see how this works. So if these are the two functions, f of x equals x cubed, g of x equals x plus 1, let's suppose we have this, f circle g of 1. What this means is we are going to take g of 1 and input that into the f function. So g of 1 gives us 1 plus 1, so that equals 2. So we're going to take 2 and we're going to input that into the f function. So f of 2 is what we need to find here. So f of 2 is just 2 to the third power, so that's 8. So what we'd say is f circle g of 1 is equal to 8. The second one, we have f of x equals x cubed. Again, g of x equals x plus 1. Let's find g circle f of 1. So we're going the other direction this time. So what we're going to do is we're going to find that we put f of 1 into the g function. So let's find f of 1 first. That's going to be 1 cubed, which is just 1. So we're going to input that value 1 into the g function. So we'll have 1 plus 1 is equal to 2. So we would say g circle f of 1 is equal to 2. Another problem here, I'll just stay on this page. F circle f of negative 1. Now what this means is we're going to take f of negative 1, and whatever we get there, we're going to put that back into the f function. So f of negative 1, we have negative 1 cubed. That's negative 1 times negative 1 times negative 1. That gives us a negative 1. So now we're going to take that, and we're going to put that back into the f function. So f of negative 1, we get negative 1 cubed, which is, again, negative 1. So what we would say is that f circle f of negative 1 is equal to negative 1. Okay, and then one last one, let's say f of g of x. So what this means is we're going to take the g function and we're going to input that into f. So what this will give us is, well, we're going to input the g function into the f function. So it's kind of like we're saying this, that's the g function, and that's going into the f function. So it's like saying g of x cubed. So this is x plus 1 cubed, which is x plus 1 times x plus 1 times x plus 1. So we'll do these first two first. That's x squared plus 2x plus 1. And then multiply that by x plus 1. If you do this and simplify, we get x cubed plus 3x squared plus 3x plus 1. So all this to say, f circle g of x is equal to x cubed plus 3x squared plus 3x plus 1. Now what we want to be able to do is, when we compose two functions, how do we find the domain of the composition? So that's what the second half of this video will be looking at. So to find the domain of composite functions, what we do is find the domain of the input function and find the domain of the composition function. The domain is the intersection or the overlap of these two. All right, so we're going to find two different domains, see where the intersection is, and that'll give us the domain of the composition. So let's let's look at two new functions. We have f of x equals x minus 1, g of x equals x over x plus 1. Find f circle g and g circle f. Missing a word here. Find the domain of f circle g and g circle f. All right, so let's do the domain of f circle g first. So the way we find this domain is we look at the input function, look at the domain of the input function, and then actually perform the composition and find the domain of the composition. The final domain is the overlap or intersection of these two. So the input domain of f circle g is the g function, because when we see f circle g, what we're doing is we're putting the g function into the f function. So before we can get to this over here, we need to do a little bit other work. So let's look at the domain of the input function. The input function is g. So the domain of g, well, I have a rational function here. We have a rational function. We want to know what makes the denominator 0. So x plus 1 equals 0. So if x is equal to negative 1, that's when we're going to have a problem. So the domain here is going to be anything except negative 1. So we'll say all x such that x does not equal negative 1. Okay? And now let's actually look at this composition, f circle g. So f circle g, let's actually perform this composition. So we're putting the g function into the f function. So in the f function, wherever we see this x, we're going to put g of x there. So g of x minus 1. And then let's replace the g of x with x over x plus 1 minus 1. So looking at this function here, f circle g of x, it looks like the only place that this is going to be undefined, again, is when this denominator is equal to 0. The only way that that is going to equal 0 is if x is equal to negative 1. So the domain here, again, is going to be all x such that x does not equal negative 1. So if we look at each of these individual domains, the domain of the input, as well as the domain of this composition, well, because they are the exact same, the overlap is just both of these. So the domain, when we combine, when we create this composition function, f of g, the domain is just going to be all x such that x does not equal negative 1. So anything except negative 1 will be in the domain of f circle g of x. And now let's go the other way. Let's get a new slide here. So let's find the domain of g circle f of x. So we already found f circle g, so we're going to go in the other direction now. So let's find the domain of f, which is the input function. Well, f is just a regular polynomial, so the domain is going to be all real numbers here. And now let's actually calculate g circle f of x. So what we're doing is we're taking the f function, and we're inputting that into the g function. So f of x over f of x minus 1. So let's multiply or substitute this in and simplify. So f of x is x minus 1 divided by x minus 1 plus 1. So we get x minus 1 over x. Now, the only place that this is going to be undefined is when the denominator is equal to 0, and the denominator will be 0 when we have an x value of 0. So whenever this is equal to 0. So the domain here, and on this one I'm going to do this on a number line. So the domain for f is all real numbers, so we're shaded everywhere here. The domain for g circle f of x, well, on here we're shaded everywhere except at 0, so there's an open circle on 0. So like this. So the overlap is everything that's shaded in each of these individual domains. So the intersection or the overlap is going to be everything here except for 0. So we're going to have an open circle, everything except 0. So writing this, we can write this in interval notation. G circle F is going to be from negative infinity to 0, union 0 to infinity, or in set notation, this is going to be all x such that x does not equal 0. Either way is appropriate for the domain of G circle F. All right, another example, we have two new functions, f of x equals square root x minus 2, g of x equals 4 minus x. So let's find the domain of f circle G. So the domain of f circle G. How we're going to do this is the input function is g, so the domain of g here, well, we take the radicand, and that has to be greater than or equal to 0. So we would say 4 is greater than or equal to x, or x is less than or equal to 4. So on the number line, we're going to say anything that is less than or equal to 4 is in the domain for G. And then let's actually do this composition. So f circle G of x. So what we're doing is we're putting the G function into the f function. So the f function is x minus 2, so in place of x we're going to put the g function. So g of x minus 2 is what we'd have there. And then let's actually just simplify this here. So because this is a radical, the radicand has to be greater than or equal to 0. So at this point now I'm actually going to write in what g of x is. So square root 4 minus x minus 2 greater than or equal to 0. I'm going to add 2 to both sides. And if I square both sides, I can remove that radical, 4, and then subtract 4 from both sides. We get 0. Divide by negative 1, I get x. Reverse the inequality when we divide by a negative. So the domain for this this composition is everything less than or equal to 0 here. So let's go over here, f circle G. If I do this on the number line, we see x is everything except everything that is less than or equal to 0. So 0, we're over here. Now looking at the intersection of these two, the intersection is going to be everything 4 and below. Oh, I have this. Let's fix this a little bit just to make these line up a little more clearly. So 0 is going to be to the left of 4. Okay, so the overlap or the intersection here is everything 0 and below. So the final domain is going to be everything from negative infinity up to and including 0. That would be the domain of f composed with G. So what's happening here is nothing between 0 and 4 is in the domain when we create this composition. Okay, so we don't include that when we look at that intersection. Now let's go the other way. So domain of G circle f of x. Now let's look at the input function. That's f. So the domain of x, the domain of f is x minus 2 greater than or equal to 0. So as long as x is greater than or equal to 2, we're good for the f function. Now let's come up with the composition. G circle f of x. So we're inputting the f function into the g function. So the g function is 4 minus x. So instead of writing x, I'm going to write f of x. And what we want is we want that radicand to be greater than or equal to 0 here. So I'll say 4 greater than or equal to f of x. Now I can replace, I could have replaced in the previous step, but we can replace the f of x with square root x minus 2. Let's come up here, just rewriting this. square both sides, we get 16 greater than or equal to x minus 2, so add 2, we get 18 is greater than or equal to x, or x is less than or equal to 18. So let's take both of these inequalities and let's write them on a number line. So first one, we're saying x is greater than 2, so 2, or greater than or equal to, I should say. So greater than or equal to 2 is like this. Less than or equal to 18 is going to be like this. So the intersection here is everything between 2 and 18. So the domain of G circle F is going to be 2 to 18, and including both of those endpoints. And let's check out one more composition. Our new functions are f of x equals x over x minus 3 and g of x equals 2 plus 5x over 2. So let's do f circle g of x first. So the input function, the domain of g, well, even though this has a fraction, there is nothing that will ever make this fraction undefined because we always have 2 in the denominator. So the domain of g is negative infinity to positive infinity. And then let's perform the composition. So might need a little more room for this. So f circle g of x. So we're going to put the g function into the f function. So the f function is x over x minus 3. So we'll say g of x over g of x minus 3, and then make the substitution. So we'll replace g of x with 2 plus 5x over 2 all over 2 plus 5x over 2 minus 3. So now we just need to simplify this complex fraction. In the denominator we have 2 and negative 3. So 2 plus 5x over 2 all over negative 1 plus 5x over 2. And then we need to get a common denominator so that we can add 2 plus 5x over 2. So the common denominator is going to be 2. We'll multiply by 2 over 2. And then same thing, multiply the negative 1 by 2 over 2. So what we get is 4 over 2 plus 5x over 2 all over negative 2 over 2 plus 5x over 2. And that gets us to 4 plus 5x over 2 all over negative 2 plus 5x over 2. Now when you have a complex fraction where the denominators are equal to each other, we can cancel out those denominators. So what we end up with over here, f circle g of x is 4 plus 5x over negative 2 plus 5x. So finding the domain, we're going to say the domain of f circle g is, well, we need to take the denominator here, find out when that is 0. So we're saying x cannot be 2/5. So if we put this expression together with this domain here, putting that all together, we're going to say the domain of f circle g is all x such that x cannot equal 2/5, cannot equal. And there we have it. So the only other thing we need to do is do G circle F, find the domain of that. So let's check that out. Alright, so let's look at the domain of the input function. So the domain of F, well, we need to know when is this denominator going to equal 0. So when x is equal to 3. So the domain here is anything except x equals 3. And then let's calculate G circle F of x. So we're going to put the F function into the G function. So this will be 2 plus 5 times f of x all over 2. Replacing f of x, we get 2 plus 5 times the f function, so x over x minus 3 all over 2. So we need to do some simplifying here. I'm going to get a common denominator between the 2 and the fraction, so multiply by 2 over 2 here. We're going to get 4 over 2 plus, this will be 5x over x minus 3 all over 2. Let's see here. So we could write this part upstairs, 5x over x minus 3. Since we're dividing by 2, that's the same as multiplying by 1/2. So we have 4 over 2 plus, this is going to be 5x over 2 times x minus 3. From here, I guess I didn't really need to get a common denominator for the 2 because these denominators are not the same. So I'll just write this as 2 plus 5x over 2x minus 6. At this point, this is probably good enough for g circle f of x. So we'll say g circle f of x equals 2 plus 5x over 2x minus 6. And we could simplify this down to one term. But for the purposes of this question, where we're just trying to find the domain, this is good enough because we just need to know, well, what's going to make this undefined? And what's going to make this undefined is when the denominator equals 0. So 2x equals 6, x cannot equal 3 here. So what we see is that this expression here matches up perfectly with this expression. So the intersection of each of these domains is just each of these individual expressions. So putting this all together, the domain of G circle F, we would say is all x such that let's do this better, such that x does not equal 3.